Right, let's carry on with part 2 of this kit build of this 5-digit frequency counter and crystal tester. Now, I got most of the components in. Next, I'm going to do the crystal for the PIC microcontroller and this little variable capacitor, which presumably can vary the crystal frequency a little bit. So, a bit of blue tack to hold that variable capacitor in while I solder it. I'm quite intrigued actually as to how much this capacitor, how much effect it's going to have on the frequency of oscillation of the crystal, which is a resonant frequency. It's mechanical, really. So I can't imagine this is going to have much effect. But we'll find out. I mean, we'll stick a crystal in the crystal tester section and see how much variation we can get on the display by turning that variable capacitor. It's interesting. Don't really know how heat sensitive variable capacitors are. You don't see variable capacitors much these days. They're not like the old days of building crystal sets and that sort of thing. I think the plates are separated by plastic separators, so they probably are a little bit heat sensitive. Now, some people have been saying, I'm interested in how accurate this frequency counter is. Well, it's as accurate as this crystal is accurate, and crystals are, by most standards, pretty accurate, a few parts per million. They vary a little bit with temperature, but not much. So I don't think accuracy is the main issue with this thing. It's going to be pretty accurate. Right, I think next I'm going to do these 3 transistors, or I probably should say 2 transistors, because I'm pretty sure the 7550 here is a voltage regulator. I think it's going to have to be, because this 5 to 9 volts input, you certainly wouldn't want to put 9 volts on the PIC. Let's take a quick look at what the PIC's absolute maximum voltage is. Right, absolute maximum ratings, voltage on VDD with respect to VSS, minus 0.3 to plus 6.5, and that's the absolute maximum. A little bit further down, it's got DC characteristics, and here we have VDD, supply voltage, maximum 5.5 volts. So certainly not 9 volts. So this 7550 is a voltage regulator. I've also traced a few tracks. Positive on the incoming socket goes to one of the pins on this thing. I think it's ground on this left side, and then in and then out. I think that's the arrangement. Now, when you put this in the board, of course, follow the flat on the package and the flat marked on the silk screen. You don't want to get this thing the wrong way round because, as I say, it's ground in, out. You don't want to get all those back to front. And as with any semiconductor component, you don't want to be spending too long with your soldering iron on these pins. I think most of them are rated for something like 10 seconds, so you can be pretty slow. Now, this 9018 transistor goes here, and it's an NPN transistor. It's a fairly high frequency transistor, and that's used to make a little oscillator in conjunction with the crystal and these two 22-puff load capacitors and these 2 resistors, so that when you put the crystal into this circuit, it just starts oscillating. Now, this is not part of the original design. This was obviously added later, and I'll talk a bit more about the original design and whose design it was and the various stages the design went through a bit later on. But let's get this 9018 transistor in there, and then the crystal oscillator section will work. Just watch out for the orientation. This one is the other way round. The flat is on the top with the regulator. The flat was on the bottom. Right, time for this DC power socket now, and it's a very sloppy fit, so that'll need to be packed up with blue tack to get that to sit straight. I might not be nerdy about resistor orientation, but I do like my socket to at least be horizontal. Now, this says 5 to 9 volts, and that's fine because it's regulated to 5 volts. However, if we put 5 volts in, and I had every intention of powering this from USB, the likelihood is this regulator will have some amount of voltage drop, and therefore we will be running the PIC at less than 5 volts. That will mean, probably won't affect the accuracy because the crystal will still resonate at its 20 megahertz frequency, but the displays might be a bit dimmer if we're running at less than 5 volts. So it's an interesting choice saying that you can go down to 5 volts, but of course it does mean that you can run from USB, which would be useful. Right, onto this 9014 transistor. It's NPN, same as the 9018. It would make sense if this was slightly higher power, because it's driving one of the display digits. It's actually driving this 5th display digit. It doesn't need to be quite as high frequency as this one, and indeed, if you look at the datasheet, it is slightly higher power and lower frequency, but not by much. But anyway, that's what the 9014 does. It's part of this circuit here with the 3 diodes, and this is, I think it's a wired NOR gate. And it's very interesting because the original design only had 4 display digits, and then a 5th one was added. And this little sort of fudge circuit, it's quite a clever fudge circuit, partially decodes the 4 driver lines that drive these 4 digits. And I think what the designer's done is, when none of these 4 are being driven, this detects that and switches on the 5th one. So it just enables a 5th digit to be used where, really strictly speaking, there aren't enough pins on the PIC microcontroller to actually do that. Interesting little bit of circuit. So let's stick that 9014 in. Right, let's stick the PIC microcontroller socket in. Now the only thing really to say about this is it's sensible to get the socket cut out. There it is, little cutout on the end there, to line up with the cutout on the silk screen, and of course the little dimple on the microcontroller. That's actually very important. Wouldn't matter particularly if this was the wrong way around. It would just be a little bit distracting. So I'm going to put that in, but I'm not going to put it in just yet because I just want to have a look at where the input line goes. And it is, well, it follows this trace here, runs up between these pins and goes to pin 3 of the microcontroller. That's pin 1 because it's the square, 2, 3. So the input goes directly into pin 3. So it's worth having a look at this PIC microcontroller to see what pin 3 actually is. Okay, so pin 3 on the PIC 16F628 is here, and it's RA4, which is an I/O port, or it's T0 clock input, or it's comparator 2. Oh, that's interesting. I thought he'd be using capture compare, which is down here, but he's not. He must be using timer 0. How interesting. So this is the T0 clock input pin, and it does route through, if you set these switches correctly, to this prescaler, timer 0 prescaler. So that's obviously how he's dividing down potentially up to 50 megahertz. Down to a frequency which can then be measured by software counter or some method. But yeah, timer 0 is what's being used here, and it does have a prescaler, so that's fine. And the prescaler does have the options of 1 to 1, 1 to 2, 1 to 4, or 1 to 8. So 1 to 4 and 1 to 8 would be adequate for measuring that very high frequency input. He's probably using the maximum prescale value 1 to 8 to give the best chance of measuring the resultant pulse width. And thinking about it, it probably is a fair bit easier to set up and use the timer 0 hardware than the capture compare hardware, so I can understand why he might have chosen to go for timer 0 rather than capture compare. Right, let's just get this. I'm running out of solder. Get this socket in. Then we can get the PIC in there. Right, let's get these two 3-pin turned pin, these things down here, sockets in. Now, interestingly, the older versions of this board had a 4th pin here marked G, which I presume was ground, and they've removed it. Is that to save one turned pin socket? Maybe. This right hand of the 3 crystal test pins is also connected to ground. You can see that there's a little link running out to this ground line running across there. So this makes a suitable ground which you can use in conjunction with in for the frequency going in. But that's very interesting that that's been removed. And once again, I'm using blue tack to try and line these sockets up as straight and as square as I can. Right, now there's just this switch, which I've since discovered goes into various menus, but it's not essential. It's not a range switch. The thing is completely auto-ranging, and I'm going to leave that off for the time being because it's very high profile and just makes fitting everything else awkward. So really it's just the displays, so let's get those in now. Now, just before I solder these displays in, I thought it might be quite interesting to see whether they're common anode or common cathode. The point is about these that there are 8 LEDs in here, the 7 segments and the decimal point, but there aren't 16 connections, so they're not all individually connectable on both the anode and the cathode. Either the anodes or the cathodes will be commoned like this. So this is common anodes. You can see all the anodes are connected to one wire, which is routed out. And these are common cathode. All the cathodes are connected to one connection, which is routed out. Now, there are 8 LEDs in here, so there should be 9 connections. There are actually 10. That's interesting. Probably you've got 2 pins doing this same common job, because inside here there are tracks running around. It's a sort of current sharing thing. If you're putting 10 milliamps through each LED and there are 8 of them, you've got 80 milliamps flowing through that common connection. So I suppose it's logical. Actually, they're probably there more for symmetry, but it does mean that you can put more current through there. But anyway, I want to find out whether these are common cathode or common anode, and I'm going to do that with a coin cell. Right, so I'm just going to run this coin cell across connections and see if anything lights up. No. Oh, yes. Yeah, something's lit up. Right, okay, so we've got negative of the cell, which is the smaller plate, actually to that middle pin, and positive to the one on the other end. No, it didn't light up like that, did it? So that middle pin must be the common one. Let's flip this cell round. Yes. So that middle pin is common, and it's common negative. So negative needs to be cathode side. So these are common cathode. Let's just try the other end. Let's see if it's the same here. Oh yes, it's the same. So it's the middle pin again. The middle pin again is negative. Is it common negative? Yes, it is. So that is also the common cathode. So common cathode goes to these 2 center pins, and then the other 2, 4, 6, 8 pins are the individual anodes of all the LEDs in that display. Now we've still got the issue of having 5 times 8, which is 40 LEDs, being driven by a chip which only has, I think, 18 pins. So how do you drive 40 LEDs from 18 pins? Well, in fact, the designer here is driving them from 12 pins, I think it is. And you use a technique called multiplexing. Now, I'm not going to go into multiplexing in any detail today because it's just too complicated, but we can look at that another time. But what it essentially means is that only some of the LEDs are on at any one time, and you put on groups of LEDs at different times, but very quickly your eye doesn't see it, and therefore you see all the LEDs lit up simultaneously, even though they're not. Now I'm just bending these peel sheets, these protective sheets, up because I don't want them to get trapped down the side of the displays. I suppose I should peel them off really, but I don't want to get them to get trapped so that I then can't get them off later. I'm also assuming that the decimal point is at the bottom when the board is this way up. There's no orientating marks on here, but it has to be this way around, and I've seen photos of it working this way up, so it would be pretty illogical to have it upside down, so I'm going to go with that. Just one display to go. It's the one that got bent, so I just need to straighten the legs on that. Can we see that? Yeah, just about. Get those legs straight so that I can drop that into the PCB. Now, shall I be nerdy and worry about the precise alignment of these displays? No, it's going to be far too much hassle. I'm just going to flip the thing over, put a bit of downward pressure on it and get soldering. And if I solder a couple of pins of each display, by moving 5. Oh, actually there are some commoning lines here, so I can see where that is. 1 pin on each display. I'm going to have to move my finger over a bit now. Then they're not going to fall out, so that's probably the easiest way to do it. Right, move my finger back. Oh, that'll be hot, won't it? Oh, now I'm in trouble. How do I get the solder over that side? Oh, I'm going to have to turn it around. And one of the pins on these displays, and I'm pressing down pretty hard as I'm doing this. I think it's that one and that one. Right, that should be them all held in, so they're not going to fall out. So now I can relax and just continue with soldering all of the remaining pins. So just work my way along here. Got a bit of blue tack holding the board down onto my mat so it doesn't slide around. And then we can power this thing up, put a test crystal in the crystal oscillator section, and see if we get a intelligible number on the display. 4 megahertz or 8 megahertz or whatever my crystal happens to be. And that will tell me that the unit is basically functioning. Then we can have a little look at the circuit in a bit more detail and possibly have a look at the original design on the designer's own website. Right, just a switch to go in, but I'm not going to bother with that yet because I don't think it's necessary initially. Microcontroller needs to go in. Now this is a bit naughty, isn't it? Putting the microcontroller, which is a CMOS device, in this polystyrene. It does have clamp diodes on all the inputs. One diode to VCC, one diode to ground, so they can to a certain extent take out or prevent static electricity build up on those pins, but I'm still just going to be a little bit careful. I'll probably just sort of try and envelop the thing with as many fingers as I can, just to kind of put resistance across the pins. I probably missed a couple there, and shove it in that socket. Right, I've got to be absolutely careful to get this the right way around, because this is probably the only component I can't actually get a replacement for, because it's a programmed microcontroller. So that looks the right way around. Let's get that into the socket. The pins are often just splayed out a bit. In fact, it sometimes helps to just put this down on the mat and bend the whole row of pins in a bit. I think that's helped a little bit. My static handling is not ideal here. Should of course have a static safe mat and wrist strap and all that stuff. Why won't this go in? I don't like these sockets. I prefer turned pin, but yeah. Okay. That's gone in. And I think now it's time to power it up. Right, I'm going to use USB 5 volts. I've got a USB to 2.1, but that won't fit in that socket. But a while ago I bought lots and lots of these in every flavour I could find, because I was just so sick of these sockets all being different sizes. This one, I've no idea what size that is, but it just seems to fit. So that fits in there. 2.1 fits in there. And now I can apply USB 5 volts. Let's do it. No preparation, everything looks good. It's powered up, and there's a 0 on the 4th digit, which I've seen on other people's videos, so I think that's pretty good. I'm just going to find a crystal now and plug it into that test socket. Right, I've got an old drawer here of crystals and resonators. I've no idea what these are, but I doubt they're very high frequency, because these come from a long time ago. Oh, that one's a 4 point. Oh, let's get in a bit closer on that. Now I've shut the blinds, so my camera's working at its maximum gain, so it'll be all fuzzy. What's that? Noise, and it'll probably change brightness. But that's a 4.9152. Wow, that'll be a challenge for this thing. 4.9152. Let's see how well it does. Put it in the oscillator section. 0. Right, it's a few hours later now, and I've been fiddling around with this thing for ages. It does work. It has to be said, it does work. Let's plug in my 5 volts. Oh, well, I say it works. 4.9152, which is exactly the frequency on that crystal, but that's probably more to do with the fact that I've been tweaking this variable capacitor to try and make it exact, which is completely stupid and pointless. I realise that. The variable capacitor is truly horrible, and I don't have a proper tool for adjusting it. A metal screwdriver is not an ideal tool for adjusting that. The crystal oscillator circuit is also horrible. It needs a modification. I'll briefly mention it in case you're building this. That 22 puff capacitor at the top there needs to be raised in value. I've put it up to 47. In order to drive the lower frequency crystals. It seems to be fine on the higher frequency crystals. Whether or not this oscillator fires up or not seems to be quite voltage dependent. At the higher voltages, it doesn't seem to fire up reliably. It does fire up reliably at, I don't know, 6 volts and below. So USB 5 volts is fine. But there are so many issues with this. And I did also want to talk about the original design, how it's been modified, how this crystal oscillator has been added, and the fact that it's actually not very good, even though the original design seems to be very good. But that's going to have to be in a third video because I'm already at 20 minutes. And so there will be a part 3. It may not be for a while because I've actually got a set of crystals coming. It's a little pack of various different frequency crystals. So I'm going to leave this for now. Yes, it works. Yes, it's got issues. And there will be a part 3. But for the moment, cheerio.